Good evening, all. Thanks for joining for today's session. Today we will be talking about the week 7 of the interactive. This is the interactive section for week 7 for the course Foundation Engineering from NPTEL. The instructor is Professor Kousik Deb. I'm one of the TAs, Kashyap Vasudevan. Uh, okay, just as usual, let us begin with a small recap. So, I request all to participate and ask or interrupt me whenever needed, and also so that we can have a active session. So, in week 7, most of the time was spent on solving problems and numericals. Many different cases were discussed by the instructor, and the major parts in the last week were the load carrying capacity of pile was discussed with respect to the critical depth concept also, which is more specific for granular soils, because the cause of this critical depth is the reason behind it is the arching effect. The arching effect is generally more predominant in granular soil. So, we discussed about that, how to consider this critical depth. So, with respect to the length to diameter ratio of the pile, we can come up with the different critical depths. And beyond the critical depth, we will assume a constant overburden pressure. So, if our depth is uh, increasing in this direction, after this critical depth, what we are to be found, the vertical stress is assumed to be constant, because if we don't consider this, we will end up overestimating the capacity at the larger depths, and which may not be true at the field. So that's why we use this concept. And the next one is layered soil. We also solved a lot of problems on layered soil. um, the critical depth concept may not be applicable. We cannot generalize it for all the soils. It is more, as I told, it's more effective. It's more seen in granular soils. So whenever layered soil comes, also it is not much of a concern. But we can check whether the depth of the layer is too significant, and if it is coming more than critical depth, we can consider the arching effect. But however, generally that layer thickness may not be that much. So in layered soils, we need not consider in many cases. But if we have a large sandy soil or a granular soil layer in between, we can check whether the depth of the layer is greater than critical. Then problems are solved on Tomlinson and Berezensev's method, Meyerhoff's method. And IS code was also discussed. How to basically the theory is same, but the values that we adopt for different constants could be slightly different. So IS code was discussed with respect to different types of piles, driven board, and also there are IS codes available for other materials also, but we are interested in concrete piles. So generally we will deal with IS code 2911 part 1 and section 1. Section 1 is specific for driven piles, cast in situ, and other sections are for other piles. And basically part 1, this is indicating part 1. Part 1 deals with material, that is concrete piles, and part 2, 3, 4 we are dealing with timber and steel, other materials. And section 1 deals with driven piles, which is in situ, and other there are other sections which deals with other board piles, etc. But basically the procedure for calculating everything is same. The constants here and there slightly differs. So yeah, that's it. And other after this, we also saw under reamed piles. So when I say under reamed piles, there can be one or multiple bulbs in the underlying pile. But basically, the idea is more or less same as we had discussed. The only difference is the interface between the concrete and the pile, or the interface that we have to consider during shearing. This is slightly different. We'll talk about that later. And at the towards the end of the week, sir in detail discussed about pile load test, which is a very important test which is done in field, because whatever calculations we do, whatever we find out using these methods, we cannot, at the end of the day, we cannot take it for granted, because it's since it is a matter of foundation, and we cannot take any chance with it. So though these things hold good for designing, after design we are supposed to test a few piles, and just confirm whether we have not over predicted the capacity or not. So pile load tests are important. So yeah, so that's it. So we'll be discussing a few problems. It could seem to be repetitive, but it's since we are dealing with different numbers, we'll get a better idea. So let's begin with this first question. Okay. So in the first question, we have a few things here. We have a pile which is driven through homogeneous stiff clay and an unconfined compressive strength of 120 kPa. So situation site conditions are such that pile length should be constricted to 15 meters. So we are given a restriction of 15 meters. So we can take the length of the pile as 15 meters. So since it is a maximum, we can go for that. What should be the diameter of the pile so that it can carry a safe load of, okay, so here this is a kind of you're supposed to find the dimension of the pile, not the capacity. We are already given the safe load, so we already know the capacity, but we are supposed to find the what could be the dimensions. So generally this is a field situation where we know what is the load coming from the superstructure, and we know the site conditions, and we are supposed to find the dimensions of the pile. Another style of the question will be to just directly find the capacity of the pipe given the dimensions of the pipe. Okay, so here I would like to point out one key thing, that is unconfined compressive strength. So here the thing is like, sometimes in the question they might give undrained shear strength, and sometimes they might say unconfined compressive strength. Sometimes they might give just a cohesion value. So please don't get confused about it. Here we if you have if you are familiar with laboratory tests, one of the popular laboratory tests is unconfined compression stress, unconfined compressive stress. So what we do is we try to we have a cell, sorry, we have a specimen, cylindrical specimen, just like a triaxial specimen, and what we do is we keep it on a pedestal, and we apply a vertical load. This is a deviator load. So in a conventional triaxial test, we have sigma 3 and sigma 1. Sigma 1 is nothing but sigma d plus sigma 3. So we will be applying pressure all around, which is sigma 3 the cell pressure. But in the UCS, what we do is we have we only have deviator stress. So sigma 3 is 0. That is the idea of UCS. So basically what happens is, in the conventional test, if we have a series of Mohr circle with different cell pressures as this, in since sigma 3 is 0, in our unconfined compressive strength, we just have one more circle which is touching the origin, because our sigma 3 is 0. That is the idea. Sigma 1 equal to sigma d. So this particular value is called, so here it is tau and sigma, tau and sigma. This is a Mohr Coulomb surface, Mohr Coulomb space. So here this point is nothing but QU. This is called unconfined compressive strength. So this particular value is quite significant, which is used to classify different soil, like especially clays, with respect to this strength. That is, when we say soft clay or stiff clay, that's what it means. So uh, so this is a important parameter. So what we need for our analysis is our cohesion, that is Cu. So this will be our cohesion, as you know, since this intercept is a cohesion and the slope is nothing but indicates our angle phi. So here, since we are dealing with clay, we have a phi equal to 0, and we can take cohesion. So this is nothing but geometrically we can say that this is nothing but half of the QU. So the diameter, half of the diameter CU is equal to QU by 2. So what's happening is here we have, they are indirectly giving us the cohesion value as 120 by 2, that is 60 kp. This is just to clarify what they are trying to say. So when they might give directly cohesion, CU directly, or they might even use this term undrained shear strength. When they say undrained shear strength, it's nothing but SU is equal to CU plus uh, tan sigma u. So here the difference is that our when we are talking about clay, it is 0, phi is 0. So we have nothing but Cu. So undrained shear strength, this is undrained shear strength. So so there is nothing to get confused. So the problem is like they might give anyway. So we might encounter these terms here and there. Even in manuals or codes, you must be careful about this. Okay. So having said that, let us move on. We have a pile. Uh, we have a pile with unknown diameter. We can take the length as 15 meter. We are said that we have Cu is equal to 60 kPa, that is 120 by 2, and what else? We know that the load is 200 kilonewton. But here there is a catch. They have given the safe load. So safe load is Qs is equal to 200 kilonewton, and so our design load that we are trying to achieve, the ultimate load that we need is nothing but we have to multiply with factor of safety, right? So generally we take 2.5 as the factor of safety here. So we can take 2.5 into 200, that is 500 kilometers. So it's better to write 500 here. Okay. So just as usual, let us write the okay. Let us write the equation that we are interested in. QU is equal to, we know basically it's deals with two terms, that is one deals with the bearing and another with the shear resistance. So let me write it as QUP plus QS. So QUP I can write it as it is nothing but the compressive like the capacity, bearing capacity of the soil at the tip, right? So at the tip of the pile, what is the bearing capacity? So we have, let us say if QUP is the bearing capacity at the tip, we have AB plus shear strength of the interface between the pile and the soil, and AS, that is the area which is undergoing shearing. So this is a basic formula. So here I can write QU as, QU is nothing but, since this we are dealing with clay soil, I can write CNC, right? If you remember our Terzaghi's equation, this is the first term that we are using. So CNC I can use, and CNC and AB. AB is nothing but since this is circular, we can use pi d square by 4, and QS, we are dealing with clay. So just by adding a new factor, that is adhesion factor, that is adhesion is nothing but the property like the shear strength between two interfaces which are two different materials. So that's when we use the term adhesion. So we have an adhesion factor, that is alpha, which is a coefficient for our cohesion, and we have AS. So AS is the shearing area, that is nothing but the perimeter of the pile into the length in which it is of the pile. So it is nothing but pi d, which is the perimeter into length. Okay. So it's quite straightforward. We can use. So here they have mentioned that Skempton's suggested by Skempton. There is nothing much to worry about it, because what he suggested was NC should be equal to 9. So that bearing capacity factor is taken as 9. So yeah. So let's write it down. Let's substitute the values. QU is equal to uh, CU is nothing but 60. NC will be 9, and AB will be pi into d square by 4. D, let us keep it as variable. And alpha was given assertion factor in the question is given as point 0.4 into Cu is nothing but 60 into pi d into L is 50. And I can write the QU as our 500. So 500 is equal to uh, 424.11 d square plus 1130.97. So we have a quadratic equation with respect to d, and if we solve that, we will get d is equal to 386.17. So we can select an answer here. The best answer, nearest answer will be 400. So 400 mm can take it as. So here, one thing that I didn't mention much was the adhesion thing. Adhesion factor, though we defined it, uh, we have to take some value, so it will generally range from it will be generally less than 1. So if it is clay versus clay, it will be just 1. So we can take Cu as it is, because the that's what the definition of cohesion is, right? So when both the materials clay, we can take it as 1. But sometimes the friction of concrete also is important, so we have to take it as accordingly. We will come to that later. So this is the adhesion factor. Okay. So and another thing that we used here is Skempton's. In Skempton's, according to Skempton, uh, suggested that our NC is equal to 9. So this is all specific for a certain cases. So this is only for circular and square pipes. Okay. Uh, Moving on. So here we dealt with a clay, uh, like in the if I'm not wrong, in the previous interactive session, the other TL, Mr. Shivshankar, he must have done with granular soil. So I thought of taking clay. So next one, we will in the next question we will deal with layered soil. Let us see what happens when layered soil comes into picture. So okay, here let us see what we got. In this question, we have a pile and a layered clay. So we have different types of clay in this question, and with different properties. So when I say properties of clay, we are interested in Cu and alpha, right? So Cu they have given indirectly, as we told before. It's given in terms of unconfined compressive strength, and alpha also they have given it straight. So we can do the same thing as we had done before. They have also told to use Scantrons. So we have the diameter, also the length. So I think we can start. Um, the length of the pile is 12 meter. Okay, so we have a pile with zero point 0.4 meter diameter, and first layer is 4, 10, 15. So we have different things: 4 meter, 10 meter, and 15 meter. Our length of the pile is 12 meters. So if I'm So yeah, I guess we can start. Now the thing is like what are the properties? So here they have given directly. So I can write a new table with CU values with in KPA, and nothing but if you remember, as I told, we can take the half of QU. So you have 20 kPa, 35 kPa, and 60 kPa. So yeah, so densities. Okay, we need not have one density. Okay, so let us start. Uh, so let's first deal with this. So our basic equation, as I told you before, is QP plus QS. So let's just start with our QUP, our bearing thing. So that is nothing but CNC plus AB. So CNC. So since we are dealing with bearing, we have to consider what is the. So here we have CU is equal to 20 kPa, 35 kPa, CU is equal to 60 kPa. And alpha is equal to 1.7. Okay, so strictly speaking, we need the exact CU value at the tip of the tip of the pile, but it's quite clear that it's in the same layer as this CU is equal to 60, so we can actually take 60, but sometimes they might give a varying CU value. So if it is varying like this, from let us say 20 to 80, then we have to take the corresponding interpolate corresponding at the corresponding depth what will be the CU value, and we'll have to take it as the CU for this at that particular depth. So having said that, we can assume it as a constant, so we can take CU as 16. So 60 into, so since it is a Skempton, we can take NC as 9 into AB. AB is nothing but our area at the bearing, right? So for bearing, we need the cross-sectional area, that is pi into d is 0.4 square by 4. Okay. So this turns out to be 67.86. Okay. Now talking about the skin friction. So we have three different layers. So we can take three different terms. So let us say I can read this QS1. I can take it as the first layer. So the first layer we have alpha 1, CU1, and AS1. Alpha 1 is nothing but 1. CU1 we have 20. AS1 is pi, d is 0.4, and length of that particular layer is 4. So we will get so this is the same for all the three cases. So I can in the same way, so I can combine this thing. The only thing changing here is our okay, alpha 1 is changing, CU is changing, and the length is changing. So I can take pi into 0.4 as common, right? So because the cross section, the perimeter is constant throughout, so I can take it as the constant. So I can combine the whole term as QS is equal to QS1 plus QS2 plus QS3. So I can take write as pi into zero point 0.4 into alpha 1 is alpha 1 CU1 into L1 plus alpha 2 CU2 L2 plus alpha 3 CU3 L3. So I'm doing this because it's repetitive, so we can directly find it. So that is pi into zero point 0.4 into alpha 1 is 1 into CU1 is 20 into L1 is 4 plus second term is uh, alpha 2 is 0.7 into CU2 is 35 into length is 6, right? 4 to 10 meter 6, then plus alpha 3, that is zero point 0.4 into what is our cu. Cu is 60. Okay, it's zero point 0.4 into 60 into 5, I think 5, 10 to 12. Okay, 2 meter. Okay, so this comes out to be 345, 35.58. So I can add both and get our q ultimate, that is uh, 67.86 plus 345.58. This is 413.43 kilometer. So to get the safe load, we can divide it by factor of safety. So that will be QU by factor of safety. That will be 413.43 by 2.5. That is equal to 165.375. Okay. So here one thing that we can observe is our cohesion in the shearing part, that the shear resistance is quite high, like when compared, so it's contributing a lot. So you can it's okay to say it's a shearing pile also, but it may not be the case for all the soils, because here in some soils this cu value might be too high, and the bearing term might be higher, this term could be higher, but in this particular case you can observe like it's like 5 times more than our bearing resistance. So you can see how important the surface of the shearing surface is contributing. So that is one thing. Another thing that we can observe here is like the alpha, the adhesion is decreasing with increase in cohesion value. That is cu value, when it is increasing, our adhesion factor is decreasing. uh, One reason for that is because actually it is laboratory proven, and it's that graph is also shown in the class if I'm not wrong. But anyway, we'll see that the is code has also adopted a particular graph which is the trend is like this. So this will be the adhesion factor and this will be the cu value. So it will be decreasing with the increase in cu. Of course, the highest value being 1. So there is the highest value is 1 and the lowest value is something like point near to point 2 or something. So we'll see that in like, but this is the both laboratorily proven and experimentally proven. Okay, so yeah, so that those are the two things I wanted to point out. Just let us solve one more similar problem, but here what is happening is we have a sand in between. So just to show how things changes, let us check this out. So here we have a concrete pile 16 meter long, layered soil stratum in such a way that this is significant because in our normal case we can have any, so realistically speaking, in the field we can have any sequence of soil, it need not be clay alone. So a different the sand, clay, it could be in any order. And okay, so one more thing here mentioned is like such a way that pile head is 1 meter above the ground level. This is also possible. So when we are driving the pile inside, and if we have achieved enough, if we have mobilized enough strength, we can stop our driving thing. Also, sometimes to get the required foundation level, we need to cut the cap of the pile. So before cutting the cap of the pile, so it might be above or below the ground level. So in this case, they have mentioned that it is 1 meter above the ground level. Okay. The subsoil profile is shown as in shown in the table. Water table is at the great depth, and if the diameter of the pile is 0.3 meter, determine the safe load. Okay, so it's very similar to what we had done before, but the small changes we have dense sand in the middle of two clays. So if you think logically, we need not worry about here much, because our bearing is well inside the third layer. So bearing term will be on clay. The other three things will come only in the shear thing. So this shear component for sand will alone be different, as we had done before. So let us see. Here we have as so here we have ground level. So 1 meter ground level we have 1 meter. So it is said that the pile is 16 meter long, so the rest of which is embedded in the soil will be only 15 meter. So that is what we can understand from the question. Okay, and the RL, the length are 4, 10 and 20. 4 meter, 10 meter and 20 meter. And we have clay, sand and clay, soft clay, dense and stiff clay. Okay, so soft clay, dense sand and stiff clay. Unit weight gamma 15 kilonewton per meter cube, gamma 1719. Okay, so 17 kilonewton per meter cube, gamma is equal to 19 kilonewton. So that's the done. Now we need QU. So QU they have given directly, so I can write CU just by taking half of it, as I told before. So I can write CU is equal to 20 kPa, and here CU is equal to 60 kPa. Okay, and alpha. Okay, here phi is 35 degree. Alpha is given as 1, and here alpha is given as 0.4. And what else is mentioned? K value is directly given. Okay. K value is given as 2. Okay, I guess we have all the ingredients we need, so we can start. So bearing thing, let us start with bearing term. So our QUP value I can write as, since it is in clay, I can use the same Skenton's thing. So CNC A base. So at the base, as I told before, we have to take the cohesion at the tip of the pile. So that is CU at the tip is 60 into NC is 9, and AB is pi into point. Okay, diameter. What is the diameter? 0.3. Okay, this is 0.3 meter diameter. So pi is 0.3 square by 4. Okay, so that will be the area of the base. Let me just clarify this. 60 into 9 into. Okay, so this value is 38.17 kilometer. Okay, so we can keep that aside. Now our concern is with the shearing resistance, right? So shearing resistance, let us check each one by one rather than what we had done before. Let us take one by one so that this is clear. So one by one. So the topmost layer, let us say QS1. We can take, since it is clay, I can write alpha 1 Cu1 As1. That will be alpha 1 is 1, Cu1 is 20, As1 is pi into zero point 0.3 into L1. L1 is nothing but our this dem, so that is 4 meter. 4 meter. This turns out to be 73 point. Sorry, 75.339. Okay, that was easy. But the next layer QS2, our shearing resistance, we have to write it as K sigma dash average into tan delta, and what else do we need? This is the the resistance into area, right? Shearing area will be AS1. So AS2 I can write. So what are those values? So we need average thing, right? So uh, average Q sigma average can be written as in IS code. It is also written as PD for your information. So I can write PD also. It's written as uh, at 4 meter depth I have 15 into 4, and at 10 meter I have 15 into 4 plus 17 into 6, and I need the average. It is 2. That is I can get it as triple one. Then in another word, words I can also say that this is nothing but the overburden pressure the middle of the layer, because since I am assuming it as linear, like it changes from 15 into 4, that is 60 kPa, to this value, right? 15 into 4 plus 17, this value to this value. I can also say it is, since it is linearly, I can just check the at that what is the thing at the 7 meter mark. I can just check the overburden pressure 7 meter mark, since we are assuming it as linear. Having said that, we can continue. So K value we have, the delta value we need, right? So what to do for delta? Delta, in the question it is said that we can assume it as 0.75. So delta is equal to 0.755, that is 0.75 into 35, 26.25 degrees. So okay, so now we have everything. So I can write QS2 as K value is 2 into our sigma average overburden pressure, effective overburden pressure is 111 into our adhesion, right? So adhesion word is used generally for our clay things, since we can visualize it as a single material. But here we can say friction. Due to friction, we have tan delta. So tan delta is interfacial friction. So that is 26.25 into, so we have stress, everything we have area is nothing but pi perimeter into pi d, that is zero point 0.3 into length, right? Length is 4 to 10 meter we have, so that is 6 meter. This turns out to be 619.08. So the last layer, that is third layer, we can do the same thing. Alpha 3 Cu3 into As3, that will be alpha 3 is 0.4, Cu3 is 60, and As3 is pi d zero point 0.3, that is into L. L will be we have 10 to 15 meter, right? So 5. This turns out to be 113.097. Okay, so if we add everything, just for shear resistance, if you add qs1 plus qs2 plus qs3, we get 75.39 plus 619.08 plus 113.097. We get it as 807.58. Okay, so we have shear resistance, so we can find the final QU is equal to QUP plus QS. That will be QU was 30. See how small value it is when compared to the shear uh, resistance. So we have 807.58. This will be 845.75. So our Q safe will be QU by factor of safety, that is 845.75 divided by 2.338.3 the value. So one among the option is 338. Okay. So that's the idea actually. In the field, say we have long pile, and there must be multiple, there can be even 4 or 5, even higher number of layers. So I guess you are in a position to now uh, come up with different the capacity using this technique. Okay, think, is there anything else? Okay, so here one thing that we are spoon fed is about, like, in the sense, these values we can get it from lab directly, laboratory, just after doing site investigation. For each layer we are getting samples from different due to different site investigation techniques, and using that samples we are getting in the laboratory, and the laboratory we are getting these values. This is done by UCS test. This you can do by either triaxial or even direct shear test depending on the problem. So okay, sorry. So this also UCS you can do. UCS, when I say UCS, I mean unconfined compressive strength test, and this you can do get it from triaxial test or direct shear test also. Like, there are different ways, as you know. So these things we can get it from laboratory. Even densities we can get it from laboratory. But these values we are getting through some uh, like literature from the correlations that we have, and other data we already have. So we need to know how to find those also. In the sense, uh, sir has already discussed about that using a table, using Brom's table. So delta and k values he has given, Brom's has given directly with respect to different pile material. IS code also suggests similar values, and in IS code we have alpha. For alpha values we have a different chart altogether. This is the one I was talking about before, with respect to cohesion value as well as alpha, our adhesion value. So you can utilize this also. We'll use this in this coming question. So let us do one more question just to do that. So we have a pile for, okay, so let us go through the question first. We have a 20-meter long pile with layered stratum. Same, the stratum is similar to what we have done before, clay, sand, clay. Okay. Water table is at ground level. That is a difference. And we have the dimension of the piles. We have to find safe layered capacity. This thing we'll check IS code. Okay. So we need alpha and our K value for our skin friction part. And yeah, okay. So just let us just have a idea about the question. Uh, what are the levels that we have? 6, 12, and 20. 6 meter, 6 meter, 12 meter, and 20 meter. The length of the pile is, okay, the length of the pile itself is 20 meters. So I guess this is the level, 20 meter. Um, let's see the properties. We have stiff clay, medium sand, medium sand, and hard clay. And CU value, this CU is 80 kPa. This CU is 300 kPa. That is quite high. That indicates it's a very good competent layer. So 5 values given as 32 degree. Okay, 8. We have densities. Gamma is equal to 18. Gamma sat, saturated density kilonewton per meter cube. Here gamma sat is also 18 kilonewton per meter cube. Here gamma sat is 19. water table is given as at ground level. Okay, so just as before, let us here also the pile is resting on clay, so we can just do the same thing that we had done before. C and C, uh, A, A, B, right? So C is 300, NC is 9 according to Skempton, and AB is pi into point. Okay, so this is 0.6 meter diameter, zero point 0.6 square by 4. This is 763.41 kilometer. Then the other, so now we need more information, right? We need that alpha value and k value. So let us first find out those things. So here we have cu of 80. So let us see in this is code, this thing, 29111, first part, first section. For 80, if I draw a line, and I think I can assume it as 5.8. So let me write alpha is equal to, sorry, not 5.8, 0.58. And next one is for clay 300. So 300 is not in there in the chart. The highest value is 200. So for higher than, so let us, we can take the lowest value available here. So that is, I guess, this much. So that I have, okay, I can take it as, it's with respect to our judgment, I'm taking it as 0.27. So it's looking very near to 3. Okay, point. Okay, let us take 0.27. So alpha clay things is clear. We can use these values. But what about our k value? So k value, if you so we can actually, so we have here medium dense sand. According to IS code, what they have suggested is, IS code is suggesting 1 to 2 well. So for medium, so for concrete piles, we can use 1 to 2 K value. He even Brahms has suggested 1 to 2. So we can take, assume it as 1.5, since we are dealing with medium sand. Since neither it is loose sand or dense sand, it's in between, you can take it as 1.5. So let's take K value is at 1.5. So now we have all the ingredients. Now we can start. But one more question arises here: what is the uh, average overburden pressure, right? So as I told before, we can find the overburden pressure for sand, because only it is required for sand, because we have that sigma average, average effective stress we required uh, at the for the layer. So instead of that, we can take at the middle of the layer. So that is nothing but sigma AV, let us say. So for the second layer, we can say it as, what do we have? Okay, so since water is at the ground level, we have to reduce the densities. So the first layer contributes 18 minus 9.81 into 6. That is the first layer. Plus the second layer will be 18 minus 9.81 into 3, right? So the middle of the layer. You can also check with the previous method. If you are using previous method, we have to find the overburden pressure at the 6-meter level and the 12-meter level, and you have to take the average. Since it is we are assuming it as linear, you will always get the same value as we are doing now. So this thing turns out to be 73.71 kPa. Okay, and that is there. Okay, done. So let us move on. So let us start with the first term, that is QS1. QS1 is equal to alpha 1 Cu1 AS1, right? Since it is clay, alpha 1 is nothing but 0.58, Cu1 is 80, and AS is perimeter into length, that is pi into 0.6 into 6. Length is nothing but 6. Okay. So this turns out to be 524.771 kPa. Sorry, not kPa, kilonewton. Okay. So the second layer we have sand, right? So sand I can write K2 sigma average 2 or PD2 in IS code, it is PD, tan delta, tan delta 2 and AS2. So K we have 1.5, this thing we have 73.71 and tan 24, right? Okay, so that I didn't mention. Here tan we need delta also. Delta is equal to 0.75 into 32, that is 24. 0.75 because we can take it as this, given by Brahms. Even in IS code, they have mentioned uh, it's on that IS code has given the freedom for the engineer to geotechnical engineer to judge which is a better way to do it, because this thing is this friction thing is quite debatable. It's a very gray area, so we can according to the confidence of the geotechnical engineer we have to choose it. So 0.75 we have taken, that is 24 on a safer side. So area is pi into zero point 0.6, right? Zero point 0.6 into, yeah, 0.6 into the length of that layer is 6 meter again. So we get a value 556.7. And third layer, QS3 is equal to again clay, so alpha 3, Cu3 and AS3. That will be alpha 3 was 0.27, Cu3 was 300, and AS3 is nothing but the perimeter into point, so that is 0.6 into 8 meter, right? So the last layer is of 8 meter. It's a very long, big section, and this turns out to be 1221.45. Just see how big this number is. So the last layer is providing a lot of shear resistance. Okay, so if you total, you get 763.41 plus 524.477 plus 556.74 plus 121.44. So you just observe here, this is like a very huge number when compared to, not quite huge, because bearing capacity also quite higher, because basically that is because our the last layer is very very strong, so even the bearing factor, bearing term is quite high. So but I wanted to emphasize on this, skin friction is very high, so that's why analyzing that becomes very important. So the total will be 366.37, and if you find our safe QUY factor of safety, that is 3066.37 divided by 2.4, this will be 548. Okay, so we have an answer. So that is the idea. So here uh, I have to say one important thing here before we wind up. Here, one important thing is in IS code, I would suggest you to go through, because in that that there is 2911. As I told, there are four different sections. All the four are very similar to each other. Only few numbers are different. One because basically it's the combination for, we have two different bored piles and driven piles, and we also have based on the basis of installation process, we have whether it is uh, sorry, this is the installation process, whether it is board or driven, and on this we have whether it is casting, whether it is cast in situ or whether it is precast. On the basis of these four combinations, we have four sections, and in these four sections, I would suggest you to go through Annexure B, Annex. In Annex B, uh, the whole whatever we are doing right now, the same concept is discussed there, and for each term, what are the values to be taken, what if for assumptions. So I would really suggest you to go through those terms, because uh, here, as I told, we have graphs for alpha and nq, and different values like k values, and what else did we find, and what to assume for delta. So all these terms, which are the values to be taken, it's mentioned there, because it will be useful in future, since we are supposed to adhere with this IS code. And there also you will find which are the gray areas in IS code, because that's left to the engineer. Then another thing that I would like to say is, if you go through the same code, there will be also uh, correlations with respect to SPT and CPT values. So if we have SPT data, we can directly arrive at different values. That is also there. So uh, yeah, so that's what I wanted to say. Then another thing is about under interpiles. Okay. I think I messed up with the spelling. Under interpiles. In this we can have two different cases. One is only at the tip we can have we will have a bulb, and one another thing is like, even at the middle we can have a bulb. So the idea is, since as I told you before, the shear resistance of the pile is quite high, right? So as we saw before, the shear resistance offered by different layers was quite high, beyond. So bearing is not nothing much contributing much. So the idea is like, if we have a bearing strata, very hard bearing strata, and nothing much is we are getting from the shear resistance, we can give a bulb at the bottom, which will drastically increase the capacity of the pipe. Because what we are doing here is, in this area, so when we are writing QUP, we write whichever method we are adopting into AB, right? So this AB is increased very very high, is increased very much, so that the capacity of the pile is increased. The construction process is quite complicated, but we have enough. It is well established in the field. Okay, this is the idea for this. But what if we have a competent layer for shear resistance also? So if we have a competent layer of shear resistance here, this idea is like, here we are increasing the shear resistance also. So the only change is with respect to this area. So in this particular layer we can write AS, right? So this is increased. So that is the idea behind underreamed pile, and the analysis is exactly the same. The only change is this area changes, right? So instead of taking the in this case, instead of taking the diameter of the pile, we have to take the diameter of the bulb. In this case, here also we have to take the diameter of the bulb. When we say pi dl, this will be the diameter of the bulb. That is the only difference. And adhesion and delta. So If we are dealing with clay, adhesion will be 1, because this interface is between clay and clay, right? Clay and clay. So this portion is it will move along with the pile when it is settling, and it will be sharing with the clay adjacent to it. So adhesion value will be 1, and when it is sand, our delta value will be equal to 5, because it's between soil and soil, sorry, sand and sand. That is the idea. Apart from that, everything will be same. Okay, so this is what I wanted to convey. uh, in this week, most of the things were solved in the lecture, so I thought of emphasizing on these things. That's why there is no much questions to discuss. So let us wind up at this thing. I would like to say that feel free to post the doubts whenever you have, or try to solve some problems. If you understand the problem solved in the sessions as well as the videos, it will be good enough. And please go through the IS code, especially the annexure B, and also get the terms very clear. So the next session will be on 17th, the coming Saturday, by Mr. Shiv Shankar Nandi, and my session will be in the next Monday. Thank you all for joining, uh, and yeah, have a nice evening. Thank you.